Hello guys, so today my topic is heart rate monitoring system using flexible printed circuit board. So moving to the topics, the topics is introduction overview of heart rate monitoring system. What is FPCBs? Role of logic gates, key logic gates used, single flow diagram expanded, benefits of using logic gates on FPCBs. Conclusion. So in this topic, we are use FPCBs and with logic gates, flip-flop, and other devices like microcontroller. So next, first of all, the introduction. Heart rate monitor track how many times your heart beats per minute. We all know that. Flexible printed circuit board. As I said before, FPCBs are thin bendable boards ideal for wearable head tech. We will discuss in board topic. Then the logic gates are basic building block that help to process electrical signals digitally inside the device. Overview of heart rate monitoring systems, sensors. Photofluorescence sensors use light to measure blood volume changes, or ECG sensors measure electrical activity of the heart. So the problem is the signal are analog and often noisy because of movement, sweat, and environment. So the need is the signal needs to be clear, digitalized, and proceed quickly, especially in the component wearable device uh, like watches and other digital device like smartphone, laptop. So first is we have to know that what is FPCB. A flex PCB or flexible printed circuit board is a type of printed circuit board made with the flexible bonded substrate instead of the rigid FR4 material type typically used in standard PCBs. Here is the photo of FPCB. This flexibility allows them to bend, folded, or even rolled up, making them ideally of applications requiring space-saving designs or where the circuit needs to conform to a curved surface. Uh, FPCB PCBs plays a crucial role in smartwatches or integrating multiple functions such as heart rate monitoring, sleep tracking, mobile payments, and Bluetooth communication. So the role of logic gates, as I said before, we use FPCB with logic gates. So in signal cleaning, row sensor signals are often wavy and inconsistent. Gate help turn them into neat square pulse. Pulse validation ensure that only real heartbeat are counted. Timing and control. Synchronize the sampling and processing. Microcontroller interface. Provide a clean digital signal that microcontrollers can easily read and calculate BPM. Next is key logic gates used. Uh, Seismic trigger circuit. Seismic trigger circuit is an electronic circuit that uses positive feedback to create the be stable to state output, often used to convert an analog signal into digital one. So the function is remove noise and ensure a clear high or low output. As I as in the sensor, we face a problem of noise. So here is the function in such mid trigger circuits, remove noise and ensure a clear high and low output. Example like a build using inverter gates. Inverter gate inverter gate means NOT gate or NAND gate with feedback. So move to the gates which are used in this project case study, and gate. Here in the photo there is mentioned in AND gate. function only allow pulse detection if multiple conditions are true. Like when the inputs is 1 and 1, then outputs will be 1. And if it is at least 1 is 0 input, then it output can be 0. So the example is pulse is above the threshold and it is the correct timing window. Here it is NAND gate and OR gates, and their function is universal gate that can perform any logic function with favor components. Example used in a simple pulse, counters, timers, and reset mechanism. Here in the picture, we see that here is a NAND gate and here is a NOR gate. So the OR gate function is allow signals from multiple sensors to be accepted. And the example is if two sensors like finger and wrist, like when we wear a watch, then it sends our wrist. Detect a pulse, either one can trigger a reading. Here is a we are also using flip-flop using NAND or NOR gate. So the flip-flop function is store information and temporarily information temporarily. And the example is flip-flop can count the number of pulse over a set time period. Its timer is 15 seconds, helping calculate BPM. So the in this case study, the D flip-flop is very useful for it. So next is signal flow diagram expanded. Here is a simple flow of operations. Sensor detects the heart pulse, then amplifier boosts the tiny signals, filter removes noise like movement artifacts. Such trigger turns noisy signal into clean pulse. Logic gates and controlling timing and validation. Microcontroller counts valid pulse, display show BPM or transmitter send it to a phone. So we are using in this case study logic gates and other microcontroller flip-flop. So the benefit of logic gates on FPCB, because we use flexible printed circuit board. So precursor, very stable pulse counting, low power, crucial for battery powered wearable device. Component design, reduce the space needed on the circuit. And the flexibility, perfect for curved surface like a wrist or chest. Here is a circuit diagram. By using microcontroller, we can create a heart rate monitoring system. Here is a microcontroller. Here display the heart rate, and this is a regulator. This is battery which provide the power, and this is heart rate sensor like wrist or chest. Here is a simple circuit. We can with a with a basic gate we can create a heart rate monitoring using FPCB. So in the explanation of this, uh, this is a represent a conceptual diagram of a heart rate monitoring circuit built using FPCB. Uh, First of all, heart rate center, bottom left corner. So So the first is heart sensor, bottom left corner. This represents a heart rate sensor which detects the electrical signals from a beating heartbeat and sends them as input to the circuit. Next is the logic gates. This simulates how the circuit processes the input signals. So first of all, top center left comparator compares two input signals to detect changes. Next Next is AND gate, output high only if both inputs are high, often used to validate a signal condition. Uh, as I said before, when inputs are 1, then output will be high, or get output high if either of its input is high. This can combine different detection conditions. NAND gate, outputs low only if both inputs are high. A universal gate of often used for fail safe or control. Output, top right corner. LED indicator represents a visual alert or output that activates in response to the proceed high signals. uh, Flexible PCB traces. The brown line simulate the conductivity parts in flexible PCB, which physically contain the gates and components. Flexible PCBs are ideal for wearable device due to their ability to bend and fit on curved surface. So the purpose of this case study is the diagram is a simplification and symbolic way to show how heart rate data can be read and proceed using digital logic implemented on flexible electronics, commonly used in wearable health monitors. So move to the conclusion. Without logic gates, heart rate monitoring would be less reliable. Combining analog signal conditioning with digital logic gates, ensuring fast, accurate, real-time monitoring. FPCBs bring everything together in a flexible, wearable form. Uh, Logic gates are fundamental in translating weak, noisy art signal into clean, reliable digital information that in the wearable device can process. As I here is the mention, without logic gates, heart rate monitoring would be less reliable. And with logical gates are fundamental in translating weak and noisy heart signal into clean and reliable digital information. That's why we are using logic gates. Logic gates are fundamental in translating weak noisy hard signal into clean, as I said before, and it can wearable device can process. So then they improve signal integrity by filtering out unwanted function and ensuring only true heartbeat are count. We know that here only true heartbeats can count. The use of seismic trigger and NAND, NOR, and flip-flop circuits provides essential control over pulse detection, timing, and data stability. PCBs enable these digital and analog circuits to be embedded into lightweight, bendable, and compact device, making continuous heart monitoring comfortable and practical. FPCBs and logic gates together lead to low power consumption, high accuracy, and durability, which are critical features in health monitoring wearables device.